Okay, so let's talk. Let's see. No, that's not what I wanted. La, la, la. It doesn't hear you. It doesn't hear you. The mic is here. Okay. Okay, so, shh. All right, number one on page 355. Here we go. Okay. Yes, I know. Go away. A certain bacterium initially increases according to the law of uninhibited growth. Huh? Exponential growth. Is that really a good population model, exponential growth for population of bacteria? Does it go off to infinity? No. Not really. Logistic is better. Remember logistic? It looks exponential, and then it levels off. That's more like it. But that's what we're doing. Part A, use a graphing utility to draw the scatter diagram for this data. Okay, how do you do that? The calculating device. Right, exactly. So let's get the Ziggy. I'll do Ziggy today. Regression on stage is a little weird. Let's not talk about that. Okay, come on, Ziggy. So enter the data. You have time in hours from 0 to 6. Okay, so let's do that. All right, so you tell me. You know how to do this. How do I enter data? Stat, edit. Right. Why is this thing stuck here? That's really not there, but all right. Okay, so how do you clear stuff that's here already? Go to the top, clear, enter, right? And same thing over here. All right, so let's enter 0 through 6. Okay. 0, enter. 1, enter. 2, enter. 3, 4, enter. 5, enter. 6. Okay. I wrote 11. Yeah, it's sticky keys. Oh, God. Sticky keys. Boom, boom, boom. All right, so let's put in the data. So we start with 1,000 bacteria already. And then we have 14, 15. Okay, 1,000. 14, 15. All right. Then it goes to 2,000 and 28, 28. Really? Okay. Follow along with your calculating device, whether it's real or virtual. Okay. 4,000 and 50. What? It's not real data. What is that? They made that up. They're making it up as they go along. Usually they have real data in these problems, but this one's made up. Okay, 8,000. All right, so how do you see the scatter plot? How do you make this? Tim? Second Y. And turn one of these on, right? All right, so scatter plot is selected. L1 and L2 is selected. It's going to graph dots. Okay, how do you make the window correct? Big enough? Zoom 9. Zoom 9. And with that's part A. Ta-da! Does it look like an exponential growth curve would fit? That's what they're going to make you do. All right. Part B, using graphing utility, fit an exponential curve to the data. All right, so how do I do that? Stat. Stat what? Calc. Which one? Is it 0? Is it? Okay, hang on. Yeah, it's 0. Okay. Okay, fine. So second one is L1, comma. Second 2 is L2, comma. And vars, y vars function 1, so it'll type it all in for you. And do we have r squared? We do. So that's a pretty good match. What's your r squared? Well, it should be a percent. Well, yeah, different calculators have slightly different round-off error, so you might not get it exactly 100, but darn close, right? Okay, you got 99.9, yeah, okay. According to this, I have 100% basically, all right, for r squared. And there's my model, and it's in fixed 3, but it's not really rounding off. And let's graph it, see what it looks like. And it's looking pretty darn close. Please excuse my screencast-o-matic, it's slowing everything down. All right, good, there you go. Now, we did ABC, and, well, C is this, right? Isn't that C? It says express the model as n of t equals n0 e to the kt. Well, instead of n of t, it's y of x. Instead of n sub 0, it's 1,000.188. And then they're not using e to the, they're using 1.414 to the. That's okay, that's fine. We don't have to do an e to the, change the base. Graph it, we did that. Now, use your function that you found in part B to predict the population at 7 hours. Now remember, the data stopped at 6. So what are we doing? Extrapolating to 7. And how do you do that? How do you do that in the home screen? Can you do it on the home screen, not the graph screen? Oh, you know stuff. Come on, Dallas. Anybody? How do you get it on the home screen? No? Vars. Y vars. Function. We have it in function 1, right? And just plug in 7. This is function notation. It means like f of 7, right? And our estimate is 11,303.879 bacteria. But 0.879 bacteria are dead. Wait, did I have my Y1? It's weird. That's the Y1, right? How come I got 11,000? Doesn't that still a little big? You got 11,000? Oh, you got a different 11,000. You got 11,000 what? 311? Really? Did you get the same B and the same A? Huh? This is Y1. Y1 parentheses, yeah. Be careful, don't type this in, because if you type it in, it's rounded off. I didn't type this in. It typed it in for me, so this number is not really rounded off. There's still more decimals after the 188. And there's still more decimals after the 1.414. Yeah. Yeah, I don't think so. Let's see. 1,000.188 times 1.414 to the 7. It did round off. Ooh, that's weird. It's not supposed to do that. Oh, I didn't think it did that. That's weird. Yeah, it's off. All right, so to avoid that, you could go mode, put it back to float, redo stuff. That, in other words, it won't round off. It's got millions of decimals, right? There they go. It still graphs out okay? Do I need ludicrous speed here? What is this? Did you have your hand up? You did. What? Well, did you type it? Okay. Did you type, let's see, that? If you just do xbreg, it automatically does L1 and L2. But if you want to have it print into Y1 for you, you have to write all this stuff out. Are you okay? Okay. Y1 is vars, Y vars function 1. Okay, so does that make a difference? Clear. I want Y1 of 7. And that's what you had? Wow, that's interesting. I didn't, fix 3 is not supposed to do that. Fix 3 doesn't do that. The Y1 is doing that. Putting it in Y1 is doing that. Okay, yeah. C? Okay. Well, they said do it as a power of E, right? They want the answer as N. Go away. Okay. N of T is N0 e to the KT, right? Is that what they said? That's not really there. Ignore that. Okay. Well, we have y of x equals y0 not e to the t, right? Yeah. So what we got was this. We had n of t is 1,000.188 times 1.44, no, 14 to the t. That's fine. They wanted you to write it in terms of e, but you don't have to. You can use what the calculator models. It's a power of rad 2 is what it looks like, right? Can you change it? Can you change it? Can you figure out what k is? Sure. If e to the k is 1.44, 414, how do you find k? ln. So you can figure out, you could write it in that form if you want to. All right, so if you ln both sides, you get that k is the ln of 414. Now what is that? That's square root of 2. So 1/2 ln 2, 1/2 0.693, 1/2 of 693 is what? 3, 4, 7? Is it 0.347? I'm rounding, I'm roughly doing that in my head. 346 is what it is? Okay. So if you want to write it in that form, you can do it. You can say n of t is n0, the initial population, which it isn't, that's an estimate, times e to the, what? E to the that. 0.347t. You could write it in that form if you want to, but this is okay. If you get this on your calculator, you could do that. Okay? All right, so we extrapolated the data from 0 to 6, we went to 7. Is that okay? Okay, good. Now, try it again. Number 9, yeah. Take a look at number 9. 9 says we want to get a model for wind chill. You know wind chill? Real feel, right? The weatherman? Okay. The following data represent the wind speed, miles per hour, and the wind chill factor at an air temperature of 15 degrees. So it's really 15 degrees out, right? It's cold. But if it gets windy, it feels colder. It's not really colder, but it feels colder. That's what this is, okay? All right, so there's your data. Use a graphing utility to produce a scatter plot. Okay. Number 9. Okay, so let's do the scatter plot. We have 5, 10, 15, 20, 25, 30, 35. Okay. Yeah, I don't know why it's saying start recording. It is recording, so that's not a problem. So stat, edit, clear stuff. What? Stat, edit, clear stuff. Okay, good. And clear stuff. Yeah, the lag is messing me up. Okay, so it's 5, 10, 15, 20, up to what? 35? Okay, so 20, 25, 30, 35. Okay. All right, so at a 5-mile-an-hour wind, it feels a little bit colder, 12 degrees instead of 15 degrees. At 10 miles per hour, it feels negative 3 degrees. Is this Fahrenheit? Yeah, Fahrenheit. Instead of 15 degrees Fahrenheit, okay? At 15-mile-an-hour wind, it feels even colder. At a 20-mile-an-hour wind, it feels even colder. This is feel. It's not the real temperature. And then negative 22, negative 25, negative 27. That good? All right, so let's do a scatter plot. Get rid of your Y1, by the way. That's going to mess you up. And then a zoom 9. And there you go. All righty. And now, so does that look like an exponential growth model? Does that look like an exponential decay model? Actually, it does. Its decay usually goes to 0, but it's going to negative something. We don't call that exponential decay. We call that exponential approach. Remember the Newton's law of heating? It's approaching room temperature if it's cold, or it's approaching room temperature from above if it's too hot, right? It's approaching not 0, right? So we don't call this exponential decay. We call this exponential approach. It's not going to 0. All righty. So we did the scatter plot. Part B, can you get a logarithmic model for this data? You can match this with a log function, apparently. It's like an exponential decay, but it's easier to match it with a log. So what do? Go to home, go to stat, calc. Where's ln? 4 is linear. That's a line. 8 is linear also, by the way. So ln, that one, okay. All right, and let's do the L1, so second L1, comma, and L2, second L2, comma, vars, y vars, function 1. Okay, and boom. And I'm in float, so I'm not going to have that round off problem. All right, and here it is. Now, if you write this down on a test paper, you can round it off, but realize you're using all those digits, okay? You can round it off to 44.198. Give me at least 3 places if it's wacky decimals. All right? And then negative 20.331. Unless you want to get into sig figs. You don't want to do that, do you? No, that's a can of worms. Don't do that. You did it today, yeah? Okay. Yeah, I'm not doing sig figs. So that's a good match. Look at that. But you knew that because of, look at your R squared, 99.8%. Again, 3 places, 0.998 or 99.8%. What? Well, because it looks like a log. Remember what logs look like? Move. This is ln, isn't it? Something like this? Well, what if you say negative ln? reflection across the x-axis. So it's a nice match, that's all. All right, so we did A, we did B. C, using the graphing utility to draw the function, well, we did. There it is, so I did it right, okay. Blah, blah, blah. And D, use this function in part B to predict the wind chill factor if it's the outside temperature is really 15 degrees, but the wind is 23 miles per hour. So is this extrapolation again? No. Stat, edit. I have values for 5 miles an hour to 35 miles an hour. They want 23 miles per hour. Is that extrapolating? No. The extrapolating would be give me 40 or give me 0. But in the range that we already have, or the domain that we already have, we call that interpolating. Just another word. So interpolate 23. How do you do that? Plug it in. Okay, how do you plug in stuff here? Bars, y bars, function 1, function notation 23. You get, it's really cold outside. Okay, so how do you write that answer? Negative 19.551 cows, chickens, monkeys, degrees Fahrenheit. Well, the wind chill, but degrees Fahrenheit. Okay, is this terrible? This is not terrible. All right, let's see. How about, any questions? We good? We're good? Okay. This is what your homework looks like. This is the homework page. How about, all right, number 3. Go back to 3. A chemistry problem. A chemist has a 100-gram sample of a radioactive material. He records the amount of radioactive material every week for 6 weeks and obtains the following data. So from week 0 through week 6, you went from 100 grams down to 45.5 grams. All right, let's enter stuff. They want the scatter plot first, right? Yep, let's do it. All right, so stat, edit, clear. What were the inputs? Okay. All right, so it's just 0, 1, 2, 3, 4, 5, 6 again. Did I double 1? No. Okay, and there. Move. All right, so it starts with 100 grams of radioactive strontium-90 or something, whatever it is. They didn't say what it is. And then 88.3. No. Okay. And 75.9. And 69.4. And 59.1. Right? And 51.8. And 45.5. Okay. What? Problem? Exponential decay. Every week. Well, let's see what it looks like. Graphically, it'll be easier to see. So what do I want to do to see this scatter plot? Zoom 9? Okay, so zoom 9. And yeah, that's the model from the last question. Get rid of Y1. Get rid of Y1. Delete that. Go back to the graph. All right, so there's your scatter plot. Well, in this domain, it's almost linear. But it's not really. It's an exponential decay curve. If you had more data, you would see it getting closer and closer, yeah. But for these few weeks, it's not getting that small that fast. You know? Yeah, part of it's linear. Any curve, even if it's really, really curvy, if you blow it up enough, it'll look like a line. If you magnify it, eventually it looks like a line.
Yeah, but back to the, can you go back to the step, to the edit, whatever. You go down 12 and then...
Down 12 and down less than 12.
And then down 6.
Okay. It's real data, man. That, you know, are you questioning his results? Is he fudging the data? The scientist says so. Whatever. Okay. Part A, do the scatter plot. Part B, get an exponential curve. Okay. So how would I get an exponential regression? Stat, calc. It was 0? Okay. All right, let's do the L1 and L2. Let's be weird. Vars, y vars, function 2. How about that? Ah, scary. Why not? Who cares? Graph. Does it match? Pretty good. Okay. All righty. And by the way, what was the coefficient of determination? R squared is about 3 places. 0.998, or as a percent, 99.8%. That's enough. Okay. All right. So C, express it as the power of E. Well, you don't have to. You could if you want. Remember we did that. Okay. D, graph the exponential function. We did that. E, from the resultant part B, determine the half-life. Aha. Now, how do you figure out the half-life? Remember, the initial quantity was how much? 100. So we want to know how much time it takes to get to what? 50. Okay, so is that an extrapolation? No, it's going to be somewhere in here, somewhere, right? So 5 point something, right? No, wait, 50? Yeah, 5 point something. You did it right? Okay. How did you do it here? Okay, y equals, what do they want? 50, okay. Well, how about I make that y1? And then you're doing super trace, right? Okay. Super trace, second trace, intersect, and 1. 2, since there's only 2 curves. 3, there's only 1 point of intersection, you don't have to guess. And it's about 5.2, yeah, well, yeah.
So to find half-life, you have the...
How long does it take to get half of the original amount?
So that you take half of the highest y value?
Half of any y value, really. It's easy to start at t equals 0 and see how, right? You could do it between any two t's and figure out the delta t if you want, right? Now, how would you write that to round it off to 3 places? 5 point what? I'm running off to 3 places. 299 rounds up, though, so 5.300 to show that you're running off to 3 places, 00, right? So 5.300 is the answer to that question. All right. Oh, by the way, we got to talk. What's going on tomorrow? Pre-testy. We have testes this week. This is the last topic right here, this chapter. Chapter 5, what? That's what I was going to talk about. All right, who wants to test on Monday? You really want to test on Monday? What's wrong with you? Who wants to test on Friday? Good, we'll have it on Friday then. No, all right, fine. You want to go to the thingy on Friday? Oh, I guess so. Oh, I get all packed in the gym like sardines and sweaty and disgusting. Okay. Pep rally. I love it, pep rally. Okay. What? Yeah, I know, really, I wish. Okay. Let's see.
Mr. Garcia, so how many
What? We usually have 2 quizzes in each chapter, so we did 2 already. Pre-test tomorrow, test on Monday. Unless you want to take the test during the pep rally in the gym. That would be interesting, no? All right, you know what? I think we're done. That's it. That's good for today. All right, so I got to save this Smart Notes and this screencast that are newly minted, never existed before. Amazing. All right, so let's go to YouTube. Say goodbye to YouTube. Bye, YouTube. Not doing bye, YouTube. Okay. Let's buy YouTube this way. Bye, YouTube. See ya.